Okay, so we're coming back to questions that we should know how to do from the exam review. Exam review number one. These are the types that will be on the final. So be able to calculate a limit. Notice we've got the limit here as h goes to 0. We can't let h go to 0 at this point because we get division by 0. So an approach that we could use is to get a common denominator in the numerator so that we can combine this fraction. So we see the first one, the first term would have the common denominator if we multiply it by the denominator at the other side, a over a, which is multiplying by 1. And we can do that anytime we want because when you multiply by 1, that's the identity element, you don't change anything. Okay, and then we've got this minus, we've got the second term, 8 over a. And what we want to multiply this one by is a plus h. So that'll give us a common denominator. We'll be able to add these together. And again, we can do this because this is another way to write 1. And then we still have this all over h. Okay, so just kind of remembering. So we end up with 8a, right? That's from this part here, over a times a plus h. And I'm not going to distribute this quite yet. Maybe we will, maybe we won't, but we'll just see. And then we're going to get a minus. Now here we're going to take this 8 and distribute it to both of these. So we'll get minus, yeah, I could maybe shorten my steps, but we'll see a plus 8h. And then we end up with a denominator a plus h. Okay, so we'll go through each of these steps all over h. Give myself a little more room here. Okay, so come back here. We've got a common denominator now. So come down here. So, and when we make the common denominator, since this negative applies to the whole fraction, it's actually going to distribute to both of these terms. So it was like, one way you could have thought is put it on first, distribute the negative 8. So we get 8a minus 8a minus 8h in the numerator. We get a denominator of a times a plus h. And instead of leaving this as a complicated fraction, we're going to divide by h, which means we're multiplying by 1 over h. Okay. Dividing by h means we're multiplying by its reciprocal. Okay, so that's hopefully clear. So then now we've got everything in a more simplified fraction. Okay, so then we keep going forward. This part here becomes 0, right? And so we're left with a fraction. I'm going to change the color slightly. Minus 8h all over a plus h times h, right? That's that part here. And we can take h divided by h is 1. So now we have negative 8 over a times a plus h. We can let h go to 0 now. And again, because we've had this limit as h goes to 0. And again, sometimes, yes, that should have been written on each of the terms, but just remember we've got it, kind of this is our scratch work, our thinking. So if I let h go to 0, what do I have? I have a times a, so I end up with minus 8 divided by a squared. And that is, because that's really, remember, this is a difference quotient that's like, this was the function 8 over a, or really our function was 8 over x. If we take this derivative, Um, this is like just kind of tying it to our uh, taking a derivative. The negative comes down, so we get negative 8. Subtract 1 from the exponent, we get x to the minus 2. We ended up with minus 8 over x squared. That's what we got here, right? So we have a little advantage now when we go back to do limits is if we can at least spot that this part is really the function we're working with. Um, this difference quotient is, y2 minus y1. Uh, or remember, it comes from that f of x plus h minus f of x all over h. So this part is the function. You could say, yeah, that makes sense. Okay. Um, on a multiple choice, could you do that? Sure. You could say, oh, I'll use calculus. But anyway, be able to take that derivative, that limit. Okay. So that's that part. Um, let's look about if we've got a function, how do we make sure it's a piecewise function? How do we make sure it's going to be continuous? Well, we could look at our theorems and such, but we've got polynomial functions here, so both pieces by themselves are continuous. So if the two pieces are going to maintain um, continuity to be continuous, where we're going to have to check is the place where they sort of hand off to each other. And we can see when x equals 2 is the handoff. We go from one function to the other as we get through 2. So if they are touching when x equals 2, then we're going to be fine. So what we're going to do is we're going to set each of these functions, pieces of the function, equal to each other when x is 2. Okay, so we're going to take the first one. Well, I'll write these. So we've got c x to the third plus x needs to be equal to 5c minus 3x. So those y values need to be equal when, I don't know why this, I maybe need to get a new pad, but anyway, when x equals 2. So we plug in 2 for x. So we're going to get c 2 to the third plus 2 needs to equal to 5c. Oops, that equals minus 3 times 2. Let's focus on this part. Get this a little further down. Okay. So this 2 to the third is 8. So we get 8c plus 2 equals 5c minus 6. Get the c's together on the same side, so we'll subtract 5c, subtract 5c. At the same time, I'm going to get the 2 to the other side because what we're doing is just solving for c, right? So subtract 2 from both sides. Do multiple things at the same time. 8 minus 5 is 3c. Negative 6, negative 2 is negative 8. Divide both sides by 3. We come up with c equals negative 8 thirds. So as long as c is equal to negative 8 thirds, we will get continuity as we pass through 2. So the function will come here at x equals 2. The handoff will be something like that. I don't, whatever those functions look like, but they will be connected there at x equals 2. They won't be coming to here like this and then picking up someplace else. Any other value of c will basically cause a jump discontinuity. So this is our answer. Okay. We make sure they're continuous so that they are touching at this point of continuity. Oh, sorry, the point where, the handoff, I'll call it, a real technical term there, right? Where one function hands off to the other function. Okay, the last type of question we're going to take a look at is calculating a limit at negative infinity. So notice this is negative infinity. Um, and there's multiple ways we can do this. What I'm going to do though is for this particular one, um, we kind of know that what becomes important is the the function with highest degree. Now, um, the text we could use algebra on this one. We could um, we could also use our calculators to graph it to see what's going to happen at negative infinity, and I think that might be a good approach. So we're just going to plug this in and see what it looks like. Now, if it just went to infinity, yeah, it's easier. We can just say x over x, and it's going to go. And how's it going to affect? Because they're both squared, it's probably going to be the same at negative infinity as infinity. But let's take a look. So we'll go to y equals. Let's clear this out. I'm going to go alpha f1, which is y equals. That will give me my sort of little fraction template. It makes it a little easier to enter these. 2x squared plus 2x. That's the numerator. Oops, so go down to the denominator and put a negative 5x squared. Come down to the line plus 7,500. Enter. Now let's go ahead and take a look at the graph. I'm going to do a zoom standard just to kind of, let's see where we're at. Coming along here, looks like it's kind of a flat function. That's kind of strange, even at, see if x is 0, yeah, I should go to 0. Did I have I wasn't expecting that, but okay, maybe it's always, so let's zoom out a little bit. Okay, there we go. So we're coming out and yeah, down in here. Certainly as it goes to, oh, see, okay, then we get this little, so there's our asymptotes, probably where the denominator equals 0. Okay. Let me do this a little bit more. So I'm going to take my x's. Probably don't need to make the y's any larger. Let's go to negative 500 and positive 500. So we're trying to get out there to see what's happening. I have a feeling it should be going towards what? Negative 2/5. There's that little thing. So yeah, it's going towards something here. And what I'm going to do is let's go to the table. It looks like I've currently my table set. No, I got it on auto. That's strange. Okay, it's giving it to me as functions. Okay. So what I want to see is what's happening as I go way back. So I'm going to go to my table set. Let's go out to negative 500. Let's have it start there and let's just see. At negative 500, we're getting to this value here, negative 0.4017. 2 over 5, right, is 0.4. And so if it was negative, it would be negative 0.4. So that's looking promising. It looks like that's kind of what we're getting to. If you took this, I think you'll get close to 0.4. And yeah, we're getting close as we go out. So here's another way. We're looking at the limit. They didn't say we had to do it algebraically, just but we could calculate it. It's going to act like 2x squared over minus 5x squared. Uh, X squared cancels with x squared because there's the same value, the same degree. So this is going to go towards negative 2/5. Okay. You could do it algebraically, but I showed basically doing it graphically, taking a look, and then numerically by going into the table and then saying, oh, yeah, that's where it's coming from to get it exact. I can't really use this decimal approximation. I could go further and further out, but you'll see. Um, I guess let's try one more. Let's go to, let's maybe go to negative. I don't know if we can go out this far, but let's put in, well, that's 10,000. Yeah, we can. And then it shows, yeah, we're at negative 0.4, which is 2/5. Okay. All right. That's the review for one. I'll do another video, separate video for test two review.